All right, now it should be recording. Everything is, they changed so many things. Okay. Well, I want to go back and pick up a few things so you can do all the homework. So I'm going to go back to page 8. So this is page 8. So we're going to take a look at x prime f of tx, xt naught equal x naught. And we're going to call this is 1.22. Okay. All right. So we saw the solution xt of 1.2.2 depend on the initial data. And hence, we may write xt t naught x naught. Okay? Okay, so the first definition is the solution xt t naught x naught of 1.2 is bounded if x, the absolute value, is less or equal to alpha that depend on t naught x naught, where alpha is a constant depending on t naught x naught. So this is, you may say, call it uniformly bounded if the t naught does not play, the initial time does not play any role, then it's uniformly bound. Anyway, another definition, we say the solution again, x t naught x naught of 1.2.2 is stable if for any other solution y of 1.2.2 with yt naught equal y naught, or may I say, we have, I'm going to continue here, if x naught minus y naught is less than delta, implies xt t naught x naught minus y t naught x naught less than epsilon. If, okay, for any epsilon positive. So basically you have a solution and you vary, all you do is vary the initial condition. And if the initial conditions stay close to each other, then the two solution, the distance between the two solutions stays close for all time. This is what it means. Okay? So let me do an example. Go ahead and look at this one for a second before I do an example. And here, of course, we are talking about t bigger or equal to 0. So t naught is bigger than 0, bigger or equal to 0. Okay? All right. So let's take a look at an example. Let's let x prime equal -1 with x of t naught equal x naught. Okay, let's make it 1. Okay? And that is 1.23. All right? So let's take this equation. X prime equal 1 with x t naught equal x naught. So this is our initial time. And then we know that t bigger or equal to t naught bigger or equal to 0. Okay? So this has a solution by integrating. This is separable. Remember, this is dx over dt equal 1. That implies dx equal dt. That implies dx equal dt or x equal t plus c. And then applying x naught equal x of t naught, that is t naught plus c. Okay. So c equal to, so we have a t naught, yeah, c equal to x naught minus t naught. So the solution is x of t naught, x naught equal to t plus x naught minus t naught. Okay? All right. So again, can easily see that the solution is unbounded since x goes to infinity as t goes to infinity. All right? Because remember, I have t plus x naught minus t naught. And remember, t naught is fixed. All right? Okay. Now, we're going to let y be another solution. So let y of t be another solution. Then y of t naught, x naught is t plus y naught minus t naught. Remember now, we are using x t naught equal y naught. Okay? So let's take a look at the difference between. So let's take a look at the difference between x t naught, x naught minus y of t naught, x naught, and that is equal to t plus x naught minus t naught minus t plus y naught minus t naught, and that is, okay? So everything cancels except x naught minus y naught. You see that? And so this would be less than delta if delta is equal to epsilon. So this is less than epsilon if delta equal to epsilon. So what you get down here, for example, so here's what you do. You get down here now, you says let delta equal to epsilon. then for x naught minus y naught is less than delta, implies from here x of t, t naught, x naught minus y of t, t naught, y naught is less than x naught minus y naught, that is less than delta, which is equal to epsilon. So hence x is stable. So you may look at it and say, whoa, here we just showed that the solution is unbounded and yet it's stable. Well, yes, it is. So if you look at a picture, so what really happened? So if you look at this picture here, this is t and this is x. Let's say this is x naught and the solution is going like this. And this is xt. And then if this is y naught, then you have another solution going like that. This is y, t, t naught. So if this is less than delta, then the difference between the two solutions is less than epsilon. You see that? This is the difference between the two solutions. So therefore, this y, by varying the initial condition slightly, that means the solution stays under control, stays very close to x. It doesn't matter what the distance between x and y, as long as y doesn't take off away from x. Okay? So that means x is stable. All right. So let's say this is out of the question now. We did that. Okay. Any questions? So now we're going to take a look at Weierstrass M-test. Weierstrass, Weierstrass-M test. And that is Lemma 1.2 on page 12. Lemma 1.2. Okay? On page 12. Let Fn be a sequence of functions defined on a set E. This is for n bigger, for n equal 1, 2, and so forth. Okay? So you have a sequence of function. Suppose there exists a constant Mn so that Fn is less or equal to Mn. That means this is a not uniform bound. That means this bound depends on the function here. Okay? If Mn n equal 1 to infinity converges uniformly, so this is a sequence now of numbers. then Fn of t, n equal 1 to infinity, converges uniformly and absolutely on the set E. Okay? So here's an example. So we have let Fn of t equal to 1 over t squared plus n squared for n equal 1, 2, and so forth. Correct? Then Fn of t, and t is in R. Let's say t is in R, in your real number. I can take it to be positive, but I really doesn't matter here. N of t is less or equal to 1 over n squared for all t belong to the real, correct? So this is your Mn. That is your Mn. You see that? Okay. All right. Now, Fmn is n equal 1 to infinity 1 over n squared, which converges. We know this converges by the p-test. Hence, so by Weierstrass m-test, 1 over t squared plus n squared converges absolutely and uniformly on R. Okay? All right. Okay? Any questions? So this is how you use the m-test, Weierstrass m-test. Okay, now we are done with this. I'm going to move on to defining a norm. How are we doing? Any questions? All right. Okay, questions. All right, a norm. This is on page. I'm going to change the definition on you a little bit because I don't want to be that general for a definition. Okay? A norm is a function that assign to every x in Rn. So x is in Rn. A non-negative real number x that satisfies the following condition. One, x bigger or equal to 0 if and only if x equals 0. Okay? That means x equals 0 if and only if x is a 0 factor. 2, alpha x is equal to alpha times the norm of x, for alpha being in R. Alpha is a constant, a real constant. Okay? And 3, the triangle inequality, x plus y is less or equal to x plus y. Okay? For y in Rn. Okay? As an example, let's let x equal to x1, x2 to xn, and let's define x to be I equal 1 to n. Okay, sorry. xi squared. Okay? So this is a norm. Okay? Another x defines a norm. Another, if I take x to be the maximum of I between 1 and n of xi, you take the maximum of all the values. For example, if you have x equal to -2, 3, -5, and 1, then under this, x is 5. Under this here. Because remember, you're taking the absolute value, so this is the biggest one. And there are other absolute, there are other infinite, there are other norms that I need you to look in the book. And I'm redoing this because there is a homework problem related to that. We will be working with norms a lot. Okay? Here, another example. Let f be a function from 0 infinity into R. Then we define the norm of f at infinity to be the supremum for all t bigger or equal to 0, the absolute value of f of t. So this is a norm. This is the infinite norm, or this is called the supremum norm. Okay? This is called the supremum. The maximum norm would be F equal to, okay, so now the maximum norm, so would be if we have F goes from A to B into R, then the maximum norm is defined by F equal to the maximum for T between A and B of F of T. Okay? So these are different examples that we will use, different norms. Any questions? All right. Now we're going to move on to chapter 2. Okay, let me elaborate on this a little bit between the maximum norm and supremum norm. For example, if you have F is a function from A to B, and this is an open interval for R, you're not going to say F is a maximum for X between A and B of F of T. Because if F is increasing, since if F is increasing, then the maximum of F does not exist. However, the supremum does and equal to F of B, the supremum. Okay? But the maximum does not exist, so we need to be careful because this is an open interval. Okay? And remember, all these has to be finite in order to have a norm. So these values have to be finite in order to have a norm. All right. Okay, now I'm going to be in chapter 2. So do you guys have access to the book now? How does it work? Yeah, I don't have the physical copy does not have any abnormality in the equation at all. So it's depend on the software. Usually the bookstore doesn't give it to you in PDF or something. I don't know. All right, because academic press is very, very picky about their books. So anyway, any questions so far? All right, chapter 2. Existence and uniqueness of solutions. Again, we're going to do some couple definition before we move on. Okay? All right, again, we are considering the initial value problem, x prime of t equal f of t x of t with x of t naught equal x naught. And I'm gonna take a look at 2.11. 2.1.1. Okay? All right. So we defined what it means to be a solution. So our interest is, so f is a function from a set D into R, okay? All right, and then f, and where D is a subset of R cross R, because we have time. Okay. Why is that? I mean, what I mean, I could have, I mean, D could be minus infinity, infinity, across minus infinity to infinity. D could be 0 to infinity, across minus infinity, infinity, and so forth. You see what I mean? So these are like a different sets, different type of a subset D of R across R. All right. Definition. This is the definition for global Lipschitz. Okay? This is a global Lipschitz. A function f from D into R is said to satisfy a global Lipschitz condition with Lipschitz constant K if f of tx minus f of ty less or equal to k times x minus y for all tx, ty in D. Okay, so this is a global Lipschitz condition. Dwell on it for a second. All right. Definition, local Lipschitz. Okay? Okay, here let me add in x. So here, a function f from D into R is said to satisfy a local Lipschitz condition in X on D if for Tx in D there is a D1 including in D, so that, okay, let me make sure I stay with the same definition. Okay, so that f of tx minus f of ty less or equal to k1 x minus y for tx ty in belong to d1. So I'm going to give an example so you can understand what I mean by that. Remember, D is restricted. So examine the solution for a second and let's talk about it. All right, let's take an example. Let's take an example. Let's let D equal to 0, 2 across R. And let f of tx equal to t times x. So basically, t belong to 0, 2. Then for ty in D, we have f of tx minus f of ty less or equal to tx minus ty, that is equal to t times x minus y, and then this is less or equal to 2 times x minus y. So this is Lipschitz. Hence, f of tx is globally Lipschitz in X with Lipschitz constant, k equal to 2. Okay? Now another example, same D, but f of tx equal to tx squared. Why don't you go ahead and see what you can do with this? Try to show its Lipschitz. Or is it globally or locally? Go ahead. All right. Well, let's take a look at it. For Tx, Ty, and D, we have f of Tx minus f of Ty equal to T of x squared minus y squared, correct? That is equal T times x plus y times x minus y. This is less or equal to 2 x plus y, x minus y. Okay? Now, I see x plus y is unbounded on D because it's R on D. And unless we restrict our domain, we F is not Lipschitz, but locally on D. So let D1 be 0 to 2 across minus L to L. So I am restricting. Then on D1, we have f of Tx minus f of Ty less or equal to, okay? On any minus L to L. This is less or equal to 2 times x plus y times x minus y. All right? So that is less or equal to 2 times 2L x minus y, which is 4L times x minus y. So K1, so this is locally. So K1 is 4L. So this is locally Lipschitz. Okay? Because we had to restrict our D to show it is not globally Lipschitz, but okay? Any questions? All right, any questions? All right, I'm gonna get rid of this stuff. So now you can see, for those of you who had other graduate classes with me, the difference in lecture and in the depth of the lecture. All right, this is not an applied math course. This is a theoretical math course. And I hope you see the difference so far. All right. So again, we're looking at x prime equal f of tx with x of t naught equal x naught 2.1.1. And then by integrating both sides, we arrive at the integral equation x of t equal x naught plus t naught to t f of s x of s dx, which is a solution of 2.1. So this is a solution to that. And okay, and this is equation 2.6. All right, you can differentiate. The derivative of that is 0. The derivative of that is f of t xt, and that's it. You get this one back. Okay? And if you put t naught, will be x naught plus t naught to t naught, that will be 0. You'll get x naught. So this is indeed is a solution. All right. So we have the big theorem. Existence and uniqueness. That means existence and uniqueness of the solution. I'm gonna have to look at my note here. So we are on the same page. It says, let D be a subset of R cross R, be defined as D equal all the set Tx such that T minus T naught less or equal to A and X minus X naught less or equal to B. Okay, where A and B are positive constant. Okay, assume that F belongs to C of D and R and satisfies Lipschitz condition. This is global. F of Tx minus F of Ty less or equal to K X minus 1. So we're gonna let M equal to the max. So this is a node of Tx belong to D of f of tx. And this is 2.17. Okay. And I'm going to continue, and h equal minimum of a and b over n. Then the initial value problem 2.1 has a unique solution denoted by x of t, t naught, x naught on the interval t minus t naught less than or equal to h, and passing through t naught, x naught. Furthermore, x of t minus x naught is less or equal to b for t minus t naught less or equal to h. So please read the statement of the theorem, and I will be back with you. I need you to understand the statement. All right, I'm back. So you saw the theorem. It's a little bit complicated, but the idea behind the theorem is what we're gonna do is we're gonna construct a sequence of function xn that exists for all time on D, and we're gonna show that the sequence converges and the limiting function satisfies the integral equation 2.16. And the limiting function with the solution of 2.11 is unique, basically. So this is what we are going to do. So I'm going to flip the board. All right. So here is our square. This is A, this is B, and there's another square, T0 minus A, T0 plus A. So this is our D1, this is our R. I'm going to call it R. So the big triangle is D, and this is R. Okay? All right. T0 minus A, T0 plus A. So we're going to start, basically, we're going to come up or build a sequence of functions xn. So we're going to start with x1, x0 of t equal x0, x1 of t equal to x0 plus t0 to t f of s x0 of s ds, and x2 of t equal x0 plus t naught to t fs x1 of s ds all the way to xn of t equal x0 plus t0 to t fs xn minus 1 of s ds. Okay, so I build this sequence. So now we need to show this sequence satisfies many other things. Okay, so let's take a look at x1 of t minus x0. That is x0 plus t0 to t f of s x0 of s ds minus x0. And that is t0 to t f of s x0 of s ds. And that is less or equal to t0 to t f of s x0 of s ds. And that is less or equal to m t naught to t ds, which is m times t minus t naught. Okay? And from here, you remember this is m is the max of the function. So this has a maximum on d, which is m. Okay? So, and 2.17, where is 2.18? 2.18 is this one. So, because the way they are defined, so this is less or equal to hm, because t minus t naught okay? HM, and M is where we had H is, so this is less or equal to B because of H. All right? Remember what H is. B over M, the minimum. Okay? All right. So we know the first iteration is less or equal to B because we need the sequence to stay in R and actually in D2. So I do another iteration. All right. So again, x2 of t minus x0 less or equal to t0 to t f of s x1 of s ds, and this is less or equal to, again, m minus t naught t ds, which is less or equal to mh, which is less or equal to b. Okay? And hence, we may continue to arrive at xn minus x0 less or equal to b as long as t minus t0 less or equal to h. T minus t naught less or equal to h. Okay? All right. You see from here, let's take a look at xn of t minus x naught. This is, again, if you look at x naught, this is less or equal to t naught to t fs xn minus 1 ds, and this is less or equal to m t minus t naught. So we have this because I need this in my estimate. Okay? I hate to erase this stuff, but I have to. But the problem is long, the proof. All right. So now, next we show the sequence xn of t converges uniformly to a function x on t minus t naught less or equal to h. Okay? So, all right, here is the trick. Let's write xn of t. That is x0 of t plus x1 of t minus x0 plus x2 minus x1 plus xn minus xn minus 1. Look, everything cancel. X0 cancel with that. X1 will cancel with that. X2 will cancel with that. Xn minus 1 will cancel with this one. You are left with xn. Or xn of t is x0 of t plus j equals 0 to n minus 1 of xj plus 1 of t minus xj of t. Okay? And let's say this is 2.1.11. And this is going to be 2.1.10 here at the end of the board, because this comes from the estimate. Okay? All right. So now we need to have control over this. So if we take the limit, as n goes to infinity, remember what we need to show, the sequence converges. So we got the limit as n goes to infinity, xn of t equal x naught of t, plus the limit as n goes to infinity, j equals 0 to n minus 1, xj plus 1 of t minus xj of t. Now, so we need to find what this is. If this converges, then xn will converge, and we will show it converges to the integral equation, which is a solution to the differential equation, to the initial value problem. Okay? All right. Let's start. So we have this. Remember, so what we need is, for j equals 0, we need x1 minus x0, but we already know what that is, x1 minus x0. Okay? So let's start at j equal 1, so we need x2 minus x1. So let's try to build. So what is x2 of t minus x1 of t? That is t0 to t f of s. This one is x1 of s minus ds minus t0 to t f of s x0 of s ds. So this is less or equal to t0 to t f of s x1 of s minus f of s x0 of s ds. This is less or equal to, remember, t0 to t k times x1 of s minus x0 of s ds. Remember that? Due to the Lipschitz condition. Now, what is x1 of s? What is x1 of s? x1 of s minus x0 of s is less or equal to ms minus, so this is less or equal to k t0 to t m times s minus t naught. S minus t naught ds. Okay? You see what happened? This is by 2.10. Okay, now this is the same as T naught to T M S minus T naught ds. Why? Because S is between T naught and T. So this is a positive. This is a non-negative number. So I can drop the absolute value. Now I can integrate this as K M S minus T naught squared over 2. Okay? From S equal T naught to S equal T, and that is equal Km T minus T naught squared over 2. You see what I did? What is the next step? The next step is J equal to 2. If I do J equal to 2, I get x3 minus x2. So the next thing is I do x3 minus x2. And this is less or equal to T0 to T F S x2 of S minus F S x1 of S ds. Now, this is less or equal to K T naught to T by the Lipschitz condition x2 of S minus x1 of S ds. But look, what is x2 of T minus x1 of T? So this is less or equal to K M over 2 times T naught to T of S minus T naught squared over 2 ds. So this is the same as Km over 2. Okay, I have K. Okay, I have K. So, and I have, okay, so I need to get this one involved. So less or equal to K times x2 minus x1 times Km. So this is gonna be like that. K squared M. So this is K squared M over 2 times T minus T0 cube over 3, which is K squared M T minus T naught over 3 factorial. Okay, now I claim that xj of t minus xj minus 1 of t is less or equal to, it's gonna be kj minus 1 is gonna be m kj minus 1 t minus t naught to power j over j factorial. Okay? Well, all we have to do is do it by induction. So we will do this by with induction. So we know it holds for j equal to 0, for j equal to 1. So then, and assume it holds for j equal to, let's see, am I using k here? So we hold for j and need to show it holds for j plus 1. Well, let's see. So if I have xj plus 1 of t minus xj of t less or equal to t naught to t f of s xj of s minus f of s xj minus 1 of s ds. This is less or equal to xj. This is less or equal to k t naught to t xj of s minus xj minus 1 of s ds. That is equal to k times m kj minus 1 over j factorial times t0 to t s minus t naught to power j ds. And that is, you integrate this s minus t naught to power j is s minus t naught to power j plus 1 over j plus 1. So this is k j m over j factorial t minus t naught to power j plus 1 over j plus 1. And so that holds. Okay? So that is m kj t minus t naught j plus 1 over j plus 1 factorial. So that's exactly what we need. Okay? All right. So let's go back to, so now we have control over this, and which is this one. So back to this. So the limit as n goes to infinity of xn of t equal x0 of t plus the limit as n goes to infinity j equals 0 to n minus 1 xj plus 1 minus xj. Xj plus 1 minus xj is mkj t minus t naught j plus 1 over j plus 1 factorial. Isn't that what I have? mkj t minus t naught to power j plus 1 over j plus 1 factorial. Guess what that is? That is less or equal to x naught plus m over k j equals 0 to n minus 1, okay, the limit. And then I'm going to have k kt minus t naught to power j plus 1 over j plus 1 factorial. And this is less or equal to x naught plus m over k times the limit as n goes to infinity will be kh to power j plus 1 over j plus 1 factorial. Since I have kj plus 1, I need to divide by this one, mkj plus 1. And so basically, So what I did is, you see, I have k to power j, but I wanted j plus 1, so I divided by k. Guess what that is? That is x0 plus m over k times e to the kh minus 1. This is what the power series of that. Okay? And that is finite. Okay? So this is finite. Okay, I will pick it up. Okay, let me finish this and say something here. And then I will stop. I'm not going to be able to finish the whole proof. I knew that. I'm surprised I got that far. Hence, by the Weierstrass M-test xn of t converges uniformly, say, to a function x of t. So next we show that xt is a solution of 2.11 on D. So that's all for today. Okay? It's a long theorem, but it's this course called Advanced Differential Equation is theoretical. So I told you last spring that even the slightest differential equation to prove the existence and uniqueness is hard. So this is one of the main theorem. It's a local theorem because on a set, the interval is limited, but it can be extended due to the continuity of f and so forth. All right, I'm stopping here. Is there any question? Let me see if there any.
I just had a quick question regarding your homework. So
Yeah.
for the homework problems, you said problems 1 through 4. I'm just trying to make sure you're referring to on that page, like exercise 1 through 4.
Yes.
Okay.
It's 1.1 through 1.4, right?
Yep.
Yeah, that's what I
Okay.
mean.
Thank you.
Any other questions? All right. Have a great day, and we will see you tomorrow. I'm going to stop recording there.